Navigation. Say it 100 times. Say it 1,000 times. And the word you would have said is... Okay, so I want to set the stage for what kind of an environment this robot will operate in. You can see, like, there's a lot of crap. I'm trying to clean stuff up over time, but I need, like, organization boxes or something to put everything in. But yeah, point is, it's just irregular. You know, there's shoes, clothes, keyboards, you know, random stuff on the ground, brake fluid, hydrogen peroxide for plants. Yeah. So, and this is a top view too. The robot will view the world differently, but yeah, like this is a hallway, doorways. This is nice because everything's like, you know, walls or a void, something weird like that. Which kind of sucks because like there's space over there, but this robot couldn't get to it. One of the things you have to consider when you write like some algorithm is like, alright, say it says it can go over here and it does go over there. Once it's over there, it has to like look around and decide if it can make it, you know, can it go over there. You know, the robot doesn't really have a goal, it's just roaming around, like maybe it gets trapped somewhere and it's just going back and forth, back and forth. But a really advanced goal, which it is hard, is to make one of those like volumetric, how do you describe it? Like photogrammetry, but it's like, you know, when they map caves, you know, it has like a depth like that. That would be crazy. I don't know how to do that. Anyway, another view. It's like, this is like a huge open space, so yeah, and again, there's like crap everywhere. I gotta throw things away. But the one thing is, like, for example, this ball, right? And these wheels, I have to make a depth scan where I can tell like the ground is just flat. There's nothing in the way. Like this should get picked up. Even though, you know, it's probably the wheels would ride right over that, but and something like that too is a problem because that would get jammed in the wheels, and detecting something like that, like a stick, yeah, that is possible with like contours, but that's not as easy as like a generic panning scan. Here's another one. There's like more crap. My cat likes to grab like random stringy things and drag them to his food bowl. It's like this nylon tube thing for a peristaltic pump. He found that from somewhere and dragged it over here. But yeah, like here it's like, alright, I'm gonna go left because I can't go these directions. It would have to get closer before it decided that, but yeah, we're talking like it can't turn around. That's when you have to just back up and hope it goes straight. Another, yeah, I gotta mop these floors again. They're muddy. But yeah, so this is nice again. It's like straight walls. So yeah, that's the kind of, you know, environment this thing will operate in and navigate. Hopefully build like a semi-scale map, you know, like a 2D one. That would be cool, but we'll see. Okay, so we're gonna do a little bit of conceptual modeling here. Here's the robot in reality, and then there's SketchUp in the background. I just did a basic one where I had the major dimensions, like how wide it is, how long the stick thing is, and then the wheels. This tail wheel is not very good. Like the rotation point, it shifts back ½ inch or it moves forward ½ inch depending on which direction you're going. But ultimately we're not that concerned about the details like that. I mean, this thing is junk, but you know, it's more of a how could you do it with crude materials, you know, and a lot of air. But anyway, so yeah, let me see, which one should I go with? We'll start with this one first. they're pretty similar. But so I made all these. Whenever I build something, I usually start by modeling the components, and then the assembly is built around that based on the component dimensions. You know, so like in order to fit everything in here, like the IMU, DC-DC boost converter, these sensors and the LEDs and everything, I had to measure them, like the servo. So I have this model here, which is like scale of what it is in reality. And then these dimensions are also scale. Anyway, these this pink thing and this yellow one, those are the sensor beams. They propagate in like a cone shape, and you know, of course, it gets larger and larger. I think I'd have to verify this, that the farther away something is, the larger it has to be for this thing to register the hit. I'm not sure if it's inside and it's smaller than the circle, it counts. But anyway, this gives you an idea of what kind of like dimensions we're working with. Because when I was talking about the floor, for example, I'm gonna, oh crap, I gotta group these together. 1 second. So if we want to scan the floor, we're gonna want to look down. Let me get a rotation. We're gonna want to look down like this and make sure like it doesn't hit itself false. And you can see there's like a maximum downwards angle it can look, something like this. And then it'll rotate about this point here. This is like really nasty SketchUp specific, but, or me specific I should say, but let me see, where is it? Give me a rotation point. This is not really gonna work. Let me draw a line here to the ground. Alright. Now we can rotate around that axis. Okay, so yeah. So this is what we're going to want to do, is like do a pan like this. And this has, you know, a vision aspect to it, but we don't have dimensions. The only dimensions we have are these distances. So, oh crap, I made this model wrong. This should be together, which I can just do this. Alright, yeah. Yeah, this is how it works, right? It'll go this way, go that way. You can kind of see like the maximum that it can turn before it like hits the wheel. So I'll have to factor that in that sweep algorithm. And also, while the IMU is supposed to capture the rotation, it's not that accurate, so I will just calibrate it with like a compass in the real world. You know, there'll just be like a compass on the ground, and I'll turn it to the specific degrees based on the width of these beams. But anyway, yeah, so when we scan this floor like this, and we get the expected values based on, you know, geometry, like here to here, say it's 9 inches, then we go farther out 11 inches. If all those values are the same, then the world is clear, right? And we're supposed to use vision, which the whole masking thing and everything, it's like to chunk the world and like make it into like boxes. It's like an object in 3D space. So the robot will be a 3D box, and then we'll be like, all right, there's some orange box over here that's this big, and the dimensions are estimated, because that's one thing that's a problem, and like what stereo vision is for. Like if you are very close to something, you know, like this. It's like, is it enormous or is it just close to you? Like, you're just looking at this. And when you look at it, like, oh, yeah, it's close to me. It's not huge. I mean, in that case, you could be moving very fast, and it is actually huge. But yeah, that's like a problem we're dealing with here, because we don't have like a point cloud that measures everything and you know exactly how big the world is. You have single points, and you have like, I don't know, say 15 points versus, you know, 1,000, so you really don't have a lot. And again, this stuff is crude. Working on this Raspberry Pi, it's crude because of my knowledge too. This is like a approachable, not academic, you know, hobby grade navigation, because I don't have a robotics background and I don't have a like CS degree or something. I work as a, I've worked several jobs as a like software engineer. It's mostly dealing with like applications or web apps or something. Right now I'm working in AI. But and that is like, I'm not developing the models, I'm consuming them, tweaking them, you know, like RAG. But anyway, yep, so that's the plan. That's what we'll be doing. Okay, so I started to figure out the angles that the panning will sweep. This is like a really tedious process, you can see. I am like eyeballing it, but pretty much I'm trying to make sure the coverage is like pretty uniform. Because if you do it like edge to edge, there's like a gap here, a gap there. Of course, like the beam is like a cone, so when you go up and scan another set, so this was 54 degrees down. Let's see. I guess the next one will be something like that. Again, I don't want it to be like that because there's gaps. Although maybe it's fine because I don't have a second, well, I guess there. This part, we'll check that, so I guess that is okay. It'll have a little bit of overlap. Yeah, let me go for where it intersects, you know, like the outer two. I'm talking about like here. So yeah, we'll go down, let's see, 35 degrees, let's say. And then I'll begin doing this again. I think I'll just match the 5 sets. Because let me see. Let's say 1, 2, 3, 4, 5. That is fine. It doesn't have to do like all the way over there, because that'll just keep growing. The farther out I scan. It's supposed to use vision, but that's still like something I have to learn. You know, it's like you. I remember I was looking at one of the Apple libraries, and it can tell like something is a floor or a table. Stretch it, maybe. Oh, God. You can tell that something is planar, a plane, you know, by the picture, and I think also because of the pings from the LiDAR. Like, you know, if you have a certain angle and you think it's a plane, you'll know the value. Anyway, yeah, so I'll do this. I guess I could have it scan all the way, but I don't know. It's just more work. And then as far as code, I'm starting to set it. This is the convention I'm going with right now. It's like 54 degrees down. This is the right set. This is the left set. It may not make sense It's not intuitive. Oh my god, I haven't been writing them down. No. I stopped writing it down. 1, 2, 3, 4. I didn't write down the last 4. I'm gonna have to go back and do that. Well, that one only has 3. This one has 4, so I didn't write down the last one. Okay, but yeah, anyway, so that's what I'm doing. And then I'm gonna take a compass in the real world and manually calibrate the servo position externally. That sucks too, but it's a servo, not a stepper with a rotary encoder. Like, I can't really trust it, you know. So yeah, do that. I guess the nice thing is the more it's angled, the more area it covers. So I'll probably just do one more set, and then that'll be the scan coverage that it looks at. Back to it. Okay, so I've drawn out all the paths. You can see how this is at 15 degrees down. Yeah, hold on a second. I just want to show this. Yeah, you can see how massive the floor cross section is at this angle. So I didn't have to do many angles on that part, just 3 at 20 degrees apart. The other ones are 15. These ones are different, I can't remember. Looks like they're roughly like 15, 20, 25, 25, 20, yeah. Those aren't as uniform as the I probably will make them uniform, but the reason that it's not symmetrical, you see that from a top view, this sensor is offset. It's not in the middle of the rotation point, so the right side, it has to turn less than to the left. But anyway, the main thing I wanted to point out with this video is the point of these scans, though, is, you know, at the center of this circle to the point of emission, that's the data you're gonna get. So it's gonna say, if you look down here bottom right, 8.3 inches. You know, so at this particular tilt and pan, that's the value we expect, which I'm gonna like calibrate that and have it be written down. That's all like trig, you know, right angle triangle. But yeah, like if you have a flat surface, you know, let's say you go to this one over here, that one is, what did it say? .6 inches. You know, so we're gonna have a bunch of those rays, and if those are all like saying it's a flat floor, it's a flat floor. If, for example, it's a ledge, then they'll shoot through the floor, you know. It's gonna say like 170 or whatever, some crazy number. It's like, alright, I should not go that direction. That's how this part of the mapping works. And then the accelerometer on board, you figure out the displacement, like as it moves forward. The robot will say, or the Raspberry Pi will tell the wheels, like, move forward 2 inches or 10 inches. And the IMU will corroborate that, you know, make sure it's, because if you're like on a spinning floor, non-carpet floor, it's probably gonna slip. So we'll have to like keep trying to go and make that distance. That's more advanced. We're still, this video is gonna be super long if I get very into the details, so I still have to actually do this in the real world, get all these values measured, and yeah, so I'm gonna do that next. Alright, so I just went through and measured all the pan and tilt angles manually that I needed based on the SketchUp work. So I first did the panning, and then now I did the tilt, which the last one I did was like 54. So you look at it like that.
I'm using parallax, like with your eyes, is kind of a problem, but I also can use it to my advantage where I center this hole here on the compass with the bearing center, and I peek to the right and make the vertical edge parallel with the compass edge here. Anyways, it's really crude, you know, but ultimately, if you have dead reckoning on the IMU, you can confirm the angles that way as well. But anyway, so this is good. What I'll do now is I'll get values in SketchUp for all the plot points. I'll put this back on the robot and I'll do a nested for loop to go over all the pan tilt combos and get measurements and see how it looks. After that, we'll plot it in ThreeJS. Okay, so I've got the head mounted back on there. I wrote some code which I'll go over after this part, but you'll see it run. It's kind of weird. I don't know why I made it this way, but it goes to the right, centers, and it goes to the left. Instead of like starting all the way in the left and going to the right. You could argue there's like less error when you do it that way, because it keeps going back to the center for half of them, but we'll see. And I did add a 1 second pause after moving because it moves so fast that it shakes. So let me hit enter on the keyboard here. And I have it returning an array of distances. See, like, alright, so this is the run. As I said, this thing is slow, man. It's not something that's like analyzing frame by frame, 60 per second real time. Like, this thing is, yeah. Alright, so we'll go over the code, what just happened. So this is the values from that last run. And these match this structure here where these are the tilt angles, and then this is right, then this is left. And because of how the, I mentioned before how the sensor is offset to the right, so it's easier to go right than left, so the left side has more angles, or it has more area, distance to travel, bigger arc. But yeah, so if you, these values are right here, so you're looking at it, it's like the same. This right here, 3, 3, 4, 4, 4, 4. That's what it means. So yeah, that's the loop right here. But let me just go over this code real quick. What did I do here? Oh yeah, I don't need this. I want decimal. I want round, round. Yeah, this stuff shouldn't have changed. Anyway, this is main so far, so when I run, you know, right here, main, I instantiate a few classes, LED, servo, the sensor. I'm not using the narrow one yet, that's the TF Mini S, because that's for longer distance, like for the blob distance measuring. So yeah, then navigation, instantiate that, you pass down those classes here. Or not, the class instances as parameters. It's not like inheritance or something. And then navigation takes in those parameters, sets them here so that the code here can access it. And here I've defined some things that aren't being used yet, like length with height, and then got these hard-coded values here, which, you know, it's not great if you try to reproduce this or change the servo or something, but again, this is like a crude project. Then, see, it says navigation. There's a blank start file, or start function here. Eventually it would actually navigate just using the depth scanning. That's something simple, like I could program something basic. But anyway, so you call scan center or scan floor, it'll center all the servos, so the beam is like parallel with the ground, the beam center line. We're talking about the, I should pull this up, sorry. We're talking about the center of the IMU, which is the rotation point. When you center, that's like exactly upright, exactly horizontal. I don't want to say exactly, it's pretty... anyway, it's manually centered, but with your eyes, my eyes. So now we're just looping over this. We loop over the X set, which is like, you know, 0 is this one. We access the tilt angle, see it right here, tilt angle. This is the right set, the left set, so 1, 2, and then create a blank array to hold the values. And then you go over the angles. So do the right side, it's going to go through these 3, and then call the sensor and store the values into here. Center it and go this one, the left set, and then the loop starts over, it increments to this set. So yeah, so we got all these values. So that's what this code is currently. Now we'll take a look at this right here and see how like far off we are. What's unfortunate too is this thing shifted. See how it's like detached from the servo, so that's kind of a source of error. See if I can move it. Yeah. That's roughly how it is, but so when I designed it, this thing's supposed to be flat, but this body's angled, so that's not great. I actually should have shimmed it upwards so it's flat with the ground. I don't want to deal with that though. So we'll just continue with what we have. Which actually is wrong. I could just offset. The offset is 4.9 degrees, like when you measure this stick with the horizon. We'll just continue with what we have and see how it goes. Yeah, you can see these are the scan patterns. So, man, let's see, 4, 3, 3, 5. Oh man, I just forgot. You have to rotate this thing. Damn, I should have did that before. You know what? I do not want to deal with that. I'm just gonna sample 1, okay? So let's say here to here is 8.35. Here to here is 12.7. And then that to there, which that part I'm not even sure about, 25. So 8, 12, 25. Our values look like that. So 8, 11, 22, 25. So I think what I'll just do is save that as like a oh, I forgot I did work in the servo too to make this work. Yeah, I'll just explain this real quick. Yeah, so I manually dialed them in, and I just made a lookup table. Like, you wanted to go 15 degrees. This is how many you subtract minus right here from the center position. What's this one? Oh, no. The center methods use the defaults. Anyway, let me put this in flat floor example. Flat floor data sample. These are, yeah, really far away. Does it make sense when it turns, it gets closer? I think it does because the arc is not perfect. Or like, it aims downwards when you go this way, it gets closer towards you. Or the response area is smaller. No, I mean, you can visually see that it's getting shorter like that. If you draw like an arc around the points here, yeah, it's a circle, which should mean it's equidistant, but is it? Say go here to here, 18. Here to here is what? 18. Yeah, that's the same. Well, as long as we're checking this. 18. Yeah, that's the same. That's not good. That is not good. It is supposed to be the same. Alright, so anyway, this is our flat floor example. If I scan like a ledge, I've seen the numbers jump to like 300, so we're good with this because I have to move on. I have to plot this in ThreeJS. And I really want to release this video today. So, I'll be using ThreeJS to make like a interface to control the robot through the web. And you can see in one of my past videos I made, you can export a 3D model from SketchUp and bring it into the web. Yeah, right here. So yeah, you can export it. And the other thing is, in this other video of mine, you can see me using ThreeJS to plot a depth scan. This robot uses the same sensors, but this is the Twerk Lidar Robot, so the entire body moves. It's kind of like a bad design, but yeah. The sensors are fixed to the frame of the robot, so it has to like tilt itself and pan itself using 12 servos. That's a terrible design for power consumption, but yeah, so you see like an open wall scan here, but this isn't what I'm going to do with this robot. I'm just trying to show that we have this like 3D, grid thing that we can use. And we'll import the robot in the middle, and then we'll build like an interface. This is like a telemetry stream from the robot. So you can see I'm designing a layout here. Telemetry stream will be right here. This will be the ThreeJS plot. You'll have a couple buttons to toggle like between the robot view and then the 2D map view. And then these will be like command buttons. And then here you can directly message the robot by strings. The Raspberry Pi, which is in the head of the robot, this is the socket you're connected to, and that's like rich in data transfer, compared to the ESP01 that's controlling the wheels. So yeah, we'll make this real quick, and I'm able to build this quickly because I've like built it in the past, and I'm a web developer, so I already know how to do that. But yeah, that'll help visualize what the robot's doing. And then these two buttons are just switching plots, which a fast way to do that is to have like two separate charts and hide them, or instances, but you can also just completely replot them from scratch. But anyway, yeah, I'll include that in this video. Alright, so there's a little bit to go over here. I exported the model right here, a basic one, and you can see it's a GLB file. I'm using Chronos. It's like a GLTF extension for SketchUp. See up here, export the GLB. Then you gotta host it somewhere, and in my case I'm just hosting it on a local Raspberry Pi Apache server. You have to have like cores enabled cross origin. But anyway, this gets loaded into the ThreeJS view here, and you can also see these orange beams. Those are matching the all of these samples here. I mentioned before how we're gonna get points, so that's what you're seeing here. These are apparently, like with WebGL, all the lines are defaulted to one thickness, so this is something I found on Stack Overflow to make thicker lines. They're actually like a spiral. But anyway, and this is mainly like a visual thing. When it's scanning, it'll with the IMU know like how far it moves once it decides to move. But when you first plop it in the world, it'll do this kind of scan and turn around on a dime and scan and see, like, you know, what its surrounding is like. And you can see here, like with those specific angles, I go down like 54 degrees, and then I go down 35, and then I go down 15, which 15 is these like super far ones. This was really problematic, and this is like just a test. But with regard to 3JS, when you plot a line, you need the two vertices, like the start and the end. That's a three-dimensional coordinate. So, for example, here this is like 15 degrees down, 20 degrees to the right, the tilt and sweep angles. And in order to get those coordinate pairs, like, you have to, you know, go here and be like, okay, that's 6.5 Y or Z. And that's the annoying thing too, is like in SketchUp and what I'm used to in the real world, like Z is blue, but in 3JS, Y is the vertical axis. So I had to screw around with that. Like when you import the model and set the grid, the camera view, like the angles are all arbitrary. Like you can decide what it is, but like default is Y is Z. So I tried to just match that, because then the camera orbit control works like as you expect. You know, dragging left, right rotates it about the green axis. But anyway, yeah, so I had to screw around with that to, you know, it's like I had to import a basic one here. It was like 000 to 111, and I'm like, alright, that's working as I expect. And you know, yeah, it's like you shoot the beam over here, what's the components? And that's just basic trigonometry, like cosine, sine, SOH-CAH-TOA, you know. Yeah, and then I had to go back and get the sensor angles, because, you know, when this thing pans and tilts, this is not fixed, like it moves around, so that's factored in as well. If you look at this closer, It's like wherever it goes, it shifts. Anyway, it's not perfect, but you can see like this contextually looks right. So now we'll just, oh, and this has a, I showed this design in the past, but I've just started to build it. I haven't gotten far, but we do have a socket connection. I disabled that because it has to be on a separate thread, which that's not hard, but regarding like async await. So so when we go to the code, see here like main, in order to get the data samples, I have this navigation code, which if you look here, I forget, like I've recorded so many like little videos. I have to put them together after this, but I forget where I am at this point. But anyway, we've got all this code right now. This is main, like this is the first thing that runs. LED, that just turns it off because there can be some like stray power in the GPIO and it'll turn it on when it starts up. So that's off. Center the servos. Just move center. Turn on the wide sensor, that's the purple one that I just showed the dimensions from. And then actually I might use the TF Mini as well, but TF Mini is for like really accurate measurements. But they're also like offset. But anyway, continuing on. Navigation, right? You feed in these are parameters, class instance parameters. You feed them into navigation. So navigation pulls those in and sets them so you can use them. We've got robot dimensions that's not used at the moment. I'll throw together a basic navigation demo, but there's going to be another video after this one because I haven't even touched the vision stuff yet. So, yeah, and this is just something I saved after I run. These are inches, and the way this data is set up, see floor scan positions, this is tilt and sweep angles. Like this is the tilt down, this is the right set, sweep to the right, left set, sweep to the left. So you'll see a video of this running, how it works, but yeah, and then there's like a delay, stop from vibration. But I probably have to change that because when it snaps all the way from the right, it like really picks up speed and it vibrates longer. So like the center call will need a longer, actually I'm gonna set that now, let's see, center, a longer delay. Well, this one doesn't matter, but yeah, I'll just put it anyway. Center. Alright, whatever. Yeah, so it takes in this to loop over it. Should call boot center right there. Again, I'm gonna add a long delay here. I don't know if I mentioned this, but this thing is gonna be slow because it's very crude, you know, low power. It's not analyzing things in real time, low data. Working with a single point, not like 10,000 concurrent or something. Anyway, so we're looping over this right here. Enumerate gives you the index being used here. Actually, no, where is that being used? Tilt ID. Oh, here. Okay. Alright, so yeah, tilt angle, so you can see when you loop over this, you're getting the angle right here, 0. And then the right angle, left angles, that's the 1, 2 here, 1, 2. And then you call the command to move, so motion tilt down. I think, let's see, where is the servo? Yeah, I added those commands in. And these I had to manually dial in, that sucked. I think I have videos of that, yeah, like where it's on the desk. This is the next day. I was trying to finish this last night, but I ran out of time, had to sleep. But yeah, so like you call tilt, the positions are mapped. Like this is the value against that. You add to it or subtract from it, depending on the direction. So that's what's happening there. And then to store the values, you call the sensor get distance, then you rebuild an array from this, which is just following the pattern like this, although it's assumed that this is that. So once you have that, we go to the client, which is what I was showing before. There's a test client for the ESP01, but that was just to make it work. This is not a sped up video, I'm just talking fast, sorry. I gotta get this done today because I have other stuff to do. So yeah, this is the basic HTML file and the style to do the layout. But you can see that a lot of this stuff is ThreeJS specific. And then this is the Chronos part, GLTF loader, Draco loader. And then this is like my custom code, the socket, the ThreeJS plotter is where the meat happens. So look at that. So this code is pretty dense. Let's just break it down. So I mentioned the exported GLB file is hosted somewhere. So this is another Raspberry Pi I have. That's like a web server using Apache. Start stuff up, the layout. This is all like I took this code from my Twerk Lidar Robot project because I had to figure this out a long time ago, how to use like ThreeJS. But pretty much I get a demo scene working and then I figure out how to plot points and lines and planes. Planes are like 4 vertices joined, and then you give it a texture, like a color. Not a texture, I haven't used textures. But yeah, so start off ThreeJS plot chart. These are all sub methods or data, but everything's in here. I'm gonna unfold this because it's hard to read it. But so ThreeJS, got your canvas. That's the top left box. I'm not trying to explain ThreeJS how it works, but just trying to shed some context on the code. The most important part, a lot of script was abandoned because, see, like I was trying to screw around with the whole axis flipping, because in the past I have flipped the axes, but then it screwed up the rotation. So it's better to just, you know, stick with it or actually figure out how to do it correctly. But this is not relevant, not relevant. This was used for my Twerk Lidar project where I plotted the mesh from the scan points. I could do that here too, but I didn't. Yeah, so we load the robot here, and then we call the plot sensor beam. Oh, and when you bring in a model, like the robot is in inches, right? But you have to convert it to meters, so that's what it's doing right here. Scaling the robot to meters. And then plot sensor beam. This is that line. So if you see, I hit save, and then I refresh. This line right here will be gone. Yeah, so that was just like a test one, simple, because it's almost like that 000111 test, but that one was just like the sensor. Anyway, I had to map things. This is why I like JavaScript. You can just throw stuff together and it'll work, you know, as far as mixing data types, you know, like string to integer or floats. And it just works. You don't have to specify the types or any of that. So these are lookups to match when you're looping over the general pattern. This was a scan I did like in my room, but the video you'll see where it's like out in the living room, the open space, that's what this is from. And actually I had this crazy one where it scanned like infinity, so I have to cap that in the future. So these are those angles you saw in Python. It loops over that, and then it pulls all the data. I mentioned to plot a line you have to have two vertices, and a vertex is XYZ. So you pull all that, it's mapped. These are the things I had to manually rotate in SketchUp and get the points. You can figure that out with math, but I'm not good at math, so I just did it the dumb way and used SketchUp. Anyway, so I got those values. These are the start vertices from the sensor, and then you've got the sensor distance, and you know the tilt and sweep angles, so you use trigonometry, you know, SOH-CAH-TOA to get those components like X, Y, Z, and then they're plotted. So that's the layout. God, this video is 17 minutes long. That's how you create this, and this layout here is like you can put a command there and send it to the Raspberry Pi. This status is the Raspberry Pi, and this will be telemetry coming in from the robot. So with this in mind, I'll just write a quick program where it like scans and then it rotates a direction, scans, rotates, and then it'll go forward, and then you'll see it run into something and turn around. There's like a, you know, this robot is like a certain size, and it's like a maximum width as far as turning. What's interesting too is like it's not a cube or a, how do you say it? The center of the robot is here, so it's like if you move 10 inches and then you spin, that part I have to figure out still. Yeah, no, I think I'll just end it here because honestly I have to move on and do other stuff. But that would be the plan, is like, so we've got this, you know, scan zone, it's clear. We can, we'll have like this angle here. We'll cut up like 360, maybe, let's see, how much is that? That looks like, I don't like how this side isn't scanned, so technically I think I'll just go here to here, and I'll cut these off. That'll reduce the scan time. Yeah, I'll probably just cut this one off because that one's kind of... maybe I'll cut these two, and then with that much you've got, let's see, 180 minus, this looks like, I don't know, 30 degrees. So I think you'd have to rotate to the left, say 120 degrees, and then this will be over here. Yeah, it's actually, it would rotate 3 times, you know, to scan a circle. Like, go this way, scan that, go this way, scan that. Maybe it has to rotate 4 times just to be sure, but yeah. Alright.